Okay, so continuing on with our video lecture for chapter 17, we were talking about in the first video lecture buffers, which is a solution that contains a weak acid and conjugate base. We also saw how to calculate the pH of a buffer solution. Now in the second video lecture, we're going to look at how to calculate the pH after you've added a strong acid or a strong base to that buffer. So here are the steps we're going to do. You're number one, determine how the neutralization reaction affects the amount of the weak acid and its conjugate base in the solution. So what does that mean? That means you have your buffer, you're adding hydroxide. After adding the hydroxide, what do you end up with? Remember, hydroxide is a strong base. It'll react with the weak acid. So we use up the acid, we have less of the weak acid, and we have more of the conjugate base. My initial pH of this acetic acid sodium acetate buffer solution is 4.74. When I add hydroxide, the pH goes up to 4.80. Now, what if I have the same buffer solution and I add some strong acid? Strong acid, again, acid and bases react. So the acid reacts with the weak base, sodium acetate, to make less sodium acetate and more acetic acid, which results in a pH of 4.68. So adding the acid, the pH goes down, but only a small amount. Adding the base, the pH goes up, but only a small amount. So we have to figure out what happens, determine how that neutralization reaction, so the acid-base neutralization reaction, affects the amount of weak acid and conjugate base in the solution. Number two, use HH to determine the pH of the new solution, because this is a buffer. Right? So this pH was calculated using HH. And we're going to look at these two steps in detail with the next practice exercise. Before we do that, we'll talk a little bit more about buffers. So buffer effectiveness, what makes a good buffer? So a good buffer should be able to neutralize moderate amounts of acid or base. That means you need to have more of the buffer than the acid or base that you're adding. And when I say adding acid or base, we always, in this chapter at least, calculate the pH of adding a small amount of either strong acid or strong base to our buffer solution. So however, there's a limit to how much can be added before the pH changes significantly. Right? You could imagine at some point you'll add so much strong acid that you're not going to have a buffer anymore. And we'll look at that. Buffer capacity is the amount of acid or base a buffer can neutralize. So how many moles of acid or base can be added before you've destroyed your buffer. And the buffer range is the pH range a buffer can be effective. So you might have a buffer that's really good from a buffer of maybe 3 to 5 pH units, but wouldn't be a good buffer for a pH of 7. So you find another weak acid conjugate base pair that could provide a buffer around 7. We'll talk about that in a minute. And the effectiveness of a buffer depends on two factors. Number one, the relative amounts of acid and base, like how many moles, and two, the absolute concentrations of acid and base. So how dilute or concentrated is the acid and base. Buffering capacity. So just a couple definitions or review topics really. A concentrated buffer, concentrated means there's a high molarity or there's a large number of the weak acid and conjugate base. Dilute, there's fewer molecules. So a better buffer is going to be concentrated versus dilute. Because you can imagine here, you only have 2 moles of the weak acid, 2 moles of the conjugate base. That means if you were to add 2 moles of strong acid, it would protonate both of these and you would only have a weak acid. There would be no more buffer. Concentrated buffer, more moles of weak acid and weak base that can react with a strong acid and strong base added. So concentrated buffer can neutralize more added acid or base than a dilute buffer, which makes it a better buffer. Effectiveness of a buffer. So a buffer will be most effective, or it'll be the best buffer, when equal concentrations of the acid and base are present. So we saw in the previous example, we had a 0.3 molar acetic acid and sodium acetate. Those are equal concentrations. If you had like a 0.3 molar of the weak acid and 0.003 molar of the conjugate base, that would not be a good buffer. A buffer will be effective when, so this is our exact ratio, when you divide the moles or the molarity of the base to the acid in your buffer, you need that range to be between 0.1 and 10. If it's lower than 0.1 or greater than 10, it's not a good buffer. And a buffer will be most effective when the acid and base concentrations are large. Again, more moles in a smaller volume, you have a better buffer. Okay, buffering range. A buffer will be effective when, so what we talked about last time, the ratio of base to acid is between 0.1 and 10. So what we can do, we can substitute this ratio into our HH equation to get the minimum and max pH. A buffer can be effective. So again, this is, remember, our HH equation. pH equals pKa plus log of the weak base over conjugate acid. And so the smallest range, plugging in this ratio as 0.1, pH equals pKa minus 1, which makes the highest range, pKa log of 10 is 1, pKa plus 1. So therefore, the effective pH range of a buffer is pKa plus or minus 1. That means if you have a buffer with a pKa of 4.20, it'll be a good buffer between 3.20 and 5.20. So 1 unit less than the pKa and 1 unit more. When choosing an acid to make the buffer, choose one whose pKa is closest to the pH of the buffer. Which brings us to practice exercise 3. Which of the following acids would be the best choice to combine with its sodium salt? Sodium salt just refers to the conjugate base. So weak acid, sodium salt is another word for its conjugate base. Salt because you've got the cation sodium and the anion is the conjugate base of the acid. To make a buffer with a pH of 4.25. So remembering you want the pKa within 1 unit of the pH. So that means that if I have a pH of 4.25, I could have, for example, a pKa of 1.95. That means I could buffer a pH between 0.95 and 2.95. So chlorous acid is definitely wrong because its pKa is too low compared to 4.25. So what I want you to do, go ahead and pause this video. Think about, of the other acids, which would be the best choice if I want a buffer of 4.25. After you think about that, hit play again and we'll go over the result together. Okay, so now the answer is, as you can see highlighted, formic acid with a pKa of 3.74. So it's closest to 4.25. We said 1.95 is too low. 7.54 is too high. The lowest pH we could buffer with a hypochlorous acid solution would be 6.54, still higher than that. Both of these would work. So nitrous acid could buffer up to 4.34, so that would work here. But formic acid is closer to the pH, so that would be the better choice. Again, looking for the pKa closest to the pH. Okay, so now we're going to look at practice exercise 4. It's 3 parts. Calculating the pH changes in buffers. A buffer is made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate, sodium is written last, to enough water to make a liter of solution. And you're given the Ka of acetic acid. So remember, molarity is moles divided by liters. So 1 liter, moles, and molarity are the same. This is a 3-part problem. A, the pH of the original buffer. B, the pH of the original buffer after adding acid. And then C, the pH of the solution that would result from adding the same moles of strong acid, this time to pure water. So we're going to look at our pH of the buffer plus acid, and then look at the difference in a pH of adding the same amount of acid to pure water. Just realize the answers are here. This is actually the answer for B, and this is the answer for C. I put A back in here. So B and C. So what I want you to do is go ahead and pause the video and answer A, the original buffer, and then play again. I'll go over A, and then I'll have you pause, do B, pause, and C. Okay, so hopefully you had time, you paused and you worked this out. The original buffer, I know a buffer, I use my HH equation. pH equals pKa plus log of weak base over conjugate acid. My pKa is 1.8 times 10 to the negative fifth, so negative log of that, plus the log of the weak base over conjugate acid. Notice how the moles and the molarity, they're the same. So the log of 1 is 0, so anytime you have the same number of moles or molarity of the weak acid and conjugate base, the pH is the same as the pKa. So then I got 4.69. Okay, so now we're looking at B, a buffer that is made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution. That just means your moles and molarity are the same. And now in part B, we want to determine the pH of the original buffer after adding 0.2 moles of HCl. So this I'll walk you through. We haven't done this before. Similar steps to my weak acid pH calculations. Number 1, write the reaction. This will be the reaction of the buffer and the strong acid. Number 2, ICN with moles. So in our previous chapter, we did ICE with molarity. Here we're doing ICN with moles, really important, moles, not molarity. Subtract the smallest number from the reactants, add to the products. So we're essentially looking at a limiting reactant problem in an icebox. An ICN, because we're not looking at equilibrium, it's going to be forward arrow only because you have a strong acid as a reactant. It's not equilibrium. Then number 3, think, what is in my beaker? How do I calculate that pH? So the reaction, step 1, whatever you're adding, either it's strong acid or strong base, that will be a reactant. And remember, acids and bases react. So my strong acid is going to react. Strong acid will react with my weak base. I'm going to use a generic equation. So my weak base, this is the acetate. My strong acid, H plus, to make HA. So net ionic equation. ICN with moles. So initially I've got 0.3 moles of my weak base, 0.3 moles of its conjugate acid, and 0.020 moles of the strong acid. My change, subtract the smallest number. So subtract the smallest number from the left, add it to the right, because you use up your reactants, make more products. And again, we're looking at a limiting reactant problem, just in an icebox. At the end, I plus C equals Z. So I use up my weak base, and I make more weak acid. So now I have step 3, think, what is in my beaker? So in my beaker at the end. So let's see, to really emphasize this. At the end, this is what I'm looking for. What is in my beaker at the end? And I can see I've got 0.28 moles of my weak base, and I've got 0.32 moles of my weak acid, conjugate acid. So what is that? It's a buffer. So think, what is my beaker? We have a buffer. Why is this so exciting? Because you do not have to use an icebox to solve for the pH. We can use our HH, Henderson-Hasselbalch, to calculate the pH of a buffer. So pH equals pKa plus log of the weak acid, conjugate base. So pH equals negative log of my Ka plus log of the weak base, so my A minus 0.28 over my acid HA. And I got 4.69. So going back to my original buffer, 4.69, here I'm adding such a small amount of my strong acid that looking at just 2 digits past the decimal, my pH doesn't even change. And that's what a buffer is. It's resistant to pH change. Okay, so now let's look at practice exercise 4C. Determine the pH of the solution that would result from the addition of 0.020 moles of HCl to a liter of pure water. So no buffer at all here, just adding HCl to water. I'm going to show the contrast. So adding the HCl to the buffer, my pH is 4.69. Now, here, I just use pH as negative log of the hydronium molarity, right? Moles of acid over the volume of solution, and I got 0.6987897, or rounded to 2 digits past the decimal, 0.70. So it was over 4.5 for adding the strong acid to the buffer. Here it drops all the way down to 0.7 if pure water, and that shows that with that buffer, it really is resistant to pH change. So in summary, the original buffer had a pH of 4.72. Adding 0.02 moles of the strong acid to this buffer resulted in a pH of 4.69. And adding 0.02 moles of the strong acid to water yields a pH of 0.70. Okay, so I realized I had a typo. Let's go back. My original buffer. The negative log of 1.8 times 10 to the negative 5th. That is my problem. This is 4.72. So I apologize. Hopefully you caught this mistake, and now you can see that you are correct. The negative log of 1.8 times 10 to the negative fifth is 4.72. When I was using my notes, I wrote down the wrong number. Apologize for that. So 4.72 with just the buffer drops down to 4.69 when you add the acid to the buffer. And then lastly, 0.70 with strong acid to pure water. Okay, so next time we'll be talking about acid-base titrations. Now that you've finished this video lecture, I want you to go on to Mastering Chemistry and work through the Mastering Chemistry assignment on this first section of Chapter 17.